Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problem number 6 of the 2010 AP Calculus AB Free Response questions. This clip is focused on differential equations, equations using tangent lines, and also the use of concavity. Okay, so let's go ahead and take a look at the A part. For the A part, we have to write an equation for the line tangent to the graph y equals f of x at x equals 1. Okay, given this information. So if we want to write the equation of a tangent line, we need two things. We simply need a point and a slope. We think back to algebra 1 and 2. The equation of a line given 2 points can be determined by using the equation y minus y1 equals mx minus x1, right? This is a point slope form of the equation of a line. We can also isolate y and write this as y equals y1 plus m times x minus x1, okay? And then the linearization variation of this equation, if we want to write this same equation using calculus notation, we can write this as a linearization of x is equal to f of a plus f prime of a times x minus a. All these three equations mean the same thing, the equation of the tangent line, all right? So we can clearly see that we need x1, y1 the point, and the slope m. So from the point given here, f1 equals 2, we can determine what x1 and y1 are. Okay, so x1 is the input 1, and y1 is the output 2. All right, so we have our points, x1 and y1. Now the slope m, in using calculus notation, is the derivative dy dx evaluated at that point 1, 2. Okay, so how do you find the derivative at that point? We'll simply plug in 1 and 2 into x and y in the differential equation. Okay, so we know that dy dx is xy to the third, so we'll just simply plug it here. 1 for x, and then 2 for y. 1 times 2 to the third. Final answer is going to be 8. Okay? All right, now that we have everything we need, we're going to write down the equation of the tangent line. Equation of the tangent line is given by y equals y1, which is 2, plus the slope m, 8 times x minus x1, which is 1. Okay, so there goes your answer for part A. All right, let's take a look at the B part. So for the B part, we are going to be making use of our answer from part A. So for the B part, we are to use the tangent line equation from part A to approximate f of 1.1. Given that f of x is greater than 0 for 1 less than x less than 1.1, is the approximation for f of 1.1 greater than or less than f of 1.1? Explain your reasoning. Okay, so let's go ahead and do that. First of all, let's find out what the approximation is, and then we'll determine if it's greater or less than f of 1.1. All right, so the B part, we are approximating f of 1.1. f of 1.1 can be approximated with the tangent line, okay? So we're going to use y of 1.1. We'll simply plug in 1.1 into the solution we got in part A. Okay, so we have 2 plus 8 times, instead of x, we have 1.1. Okay, minus x, minus 1. And then we'll go ahead and solve that. So we're going to have, this is going to become, using order of operations, 2 plus 8, 1.1 minus 1 is 0.1. Multiply that out, you have 2 plus 0.8, and the approximation is 2.8. So the question now is this approximation using the tangent line, is it greater than or less than f of 1.1, the exact value? So let's just go over some information real quick, some important points. We're going to have to make use of the second derivative, okay? So how does the second derivative connect to the value of our estimation? Let's go ahead and go over that. Now, if the second derivative, f double prime, is greater than 0 or positive, then that implies that the function is concave what? If it's greater than 0, it's concave up. If a function is concave up, then all the tangent lines will reside below the function. Okay, so if you have a graph like this, if you have a concave graph, concave upward graph, your tangent line is going to be, wherever you draw it, is going to be underneath the function when you go away from the point of tangency. Okay, so if you have concave up, your tangent line, if you use it to make an estimation at any point near the tangent line, you're going to have an underestimation. This would be an underestimate, or it's going to be less than the actual value. Okay, so you want to keep that in mind. And then the reverse, if f double prime is less than 0 or negative, then the function is going to be what? If the second derivative is negative, the concavity is going to be downwards. Okay, and if you have a downward facing concavity, your tangent line, the estimation of the tangent line at a point around the point of tangency is going to be above the actual function. In that case, you will have an overestimate. Okay, so concave up, underestimate; concave down, overestimate. Okay, so this is going to be an overestimation, overestimate, or it's going to be greater than the exact value. So in this problem, all we have to do is figure out what the sign of the second derivative at the point of tangency is, and then we can determine if it's going to be greater or less. Okay, so let's go ahead and do that. So we have f double prime of x is, oh, that's not the notation. They used the other notation right there. Let's use the notation that we had. So the square y dx square, second derivative, we're going to evaluate it at 1, 2. Okay, but before we do that, let's write it down. The function we're looking at is y to the third times 1 plus 3x squared y squared. So what is the second derivative at x equals 1? We know that when x equals 1, y is 2. So we're going to plug in these values into the second derivative equation. 2 to the third times 1 plus 3 times 1 square times 2 square. We don't even have to work this out. We can clearly see that this is going to be positive and this whole thing here will be positive. So our answer is going to be positive, which means our second derivative is greater than 0. Okay? So if the second derivative is greater than 0, the function is going to be concave up. So our tangent line will lay underneath or below the curve, which results in an estimation that's less than the actual value. Okay? So we're asked to explain our reasoning. So let's go ahead and explain what our reasoning is, our answer and the reasoning. So the approximation, let's write this down, the approximation was y of 1.1 which is equal to 2.8, is less than f of 1.1, the actual value. Well, why is that? Because on the interval on 1 less than x less than 1.1, the second derivative is positive, which results in an upward concavity, and the tangent line being below the curve, okay, being below the curve, okay. Hence, the tangent line approximation will be less than the exact value, okay, less than the exact value. Okay, so that's that. So for part C, we're asked to find the particular solution of the differential equation. Let's scroll up and take a look at that. We're going to find the particular solution of the differential equation with the initial condition f of 1 equals 2. All right, so this is a strategy, the one provided here. That's the strategy we're going to be using to solve the differential equation, okay? So the differential equation is dy dx equals xy to the third. This is going to be solved by separation of variables. So step one, you want to separate the variables. You want to have the x's on the right and the y's on the left. After separation, you integrate both sides using the appropriate integration rules. And then part 3 will use initial condition to resolve sign ambiguities if there are any, and also to find the value of c. Okay, and then plug the value of c back into the equation to get our final result. Okay, so the integration rule that we are going to be using in this problem is the power rule. The integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus our constants n plus 1 plus our constant c. Okay, all right, so let's go ahead and carry out step 1, separate the variables. So how do we do that? We need the dx on the right, so multiply both sides by dx. And then we need y to the third on the left side, so divide both sides by y to the third. Okay, so what results? The dx's divide out to 1 on the left side, and on the right side, the y to the third divide out to 1. And then we have 1 over y to the third dy equals x dx. Now, to integrate, the left side doesn't look like a power. It looks a little bit complicated. So we can make use of our properties of exponent to express this rational as a power. So we're going to use the reciprocal property. Okay, if we apply that here, we will have y to the third, y to the negative 3 dy equals x dx. Now we are ready to integrate both sides using the power rule that we have on the right. Okay, so let's go ahead and find the integral. That's the only way we can get rid of this dx and dy. The antiderivative on the left side is going to be y to the negative 3 plus 1, which is negative 2, over negative 3 plus 1, which is negative 2. That equals x to the 1 plus 1, which is 2, over 1 plus 1, which is 2, plus c. Now this c is a combination of the c's from both sides, so it's customary to put it on just one side of the equation. Okay, now we can rewrite this. We have a negative exponent here. We can rewrite this as 1 over negative 1 over 2y squared equals x squared over 2. So after integration, this is a convenient place to find what c is. Okay, so how do we find that? We're done with steps 1 and 2. Step 3 tells us to use the initial condition. Okay, so what is our initial condition? The initial condition is that f of 1 equals 2. So f of 1 equals 2. What does this tell us? Well, it tells us that x is 1 and y is 2. It's just a point, okay? This is your x, your input, and your output is y. So we plug that in here. So we're going to have negative 1 over 2. Instead of y, we put in 2 square equals 1 square over 2 plus c. Okay, and then we'll just go ahead and find out what the value of c is. Let's go ahead and do that. On the left side, if we simplify it completely, we'll have negative 1 over 8. On the right side, we'll have 1 over 2 plus c. And then c is going to be subtract 1 half from both sides. We'll have negative 1 half minus 1/8. We'll find the LCD times this by 4 top and bottom. You have negative 4 over 8 minus 1 over 8. Combine both of them, you have negative 5 over 8 as your value for c. Okay, now remember we're done after we have y isolated. So what we're going to do now is take this c value and substitute it right here. Okay, now let's go ahead and do that. That's going to yield negative 1 over 2y squared equals x squared over 2 minus 5 over 8. All right, so next what we're going to do is multiply both sides by negative 2. We'll multiply both sides by negative 2. Negative 2. And multiply this entire thing by negative 2. So what results? On the left side, we will have 1 over y squared. And then on the right side, we'll have negative x squared plus, and then if you just multiply 2 by this, the 2 goes into the 8 5 times, 5 over 4. Okay, now we can write this as a fraction, 5 over 1. Combine these two, we can multiply it by 4 top and bottom. Combine the left side, the right side, since I will be reciprocating very soon. 1 over y squared equals, we can switch this around, 5 minus 4x squared over 4. Okay, so this is just 4x squared over 4. Negative 4x squared over 4 plus 5 over 4 is negative 4x squared plus 5 over 4. So I just switched it around and wrote it like this. Okay. All right, so what we're going to do next, we're just simply going to reciprocate both sides of our equation. So just reduce both sides to the negative 1 power. And that yields y squared equals 4 over 5 minus 4x squared. And then to finish it off, we just take the square root of both sides, take square root, take the square root of the numerator and the square root of the denominator. And that gives us our final answer, which is y equals 4, actually square root of 4 is 2, so square root of 4 is 2, 2 divided by the square root of 5 minus 4x squared. Okay? If you want to state the domain, you don't have to, the problem doesn't ask you to state the domain, but if you want to do extra work, you can do that. So the domain, basically, this radicand, 5 minus 4x squared has to be greater than 0. You can't take the square root of a negative number. And then you also have it in the denominator, so you cannot even take the value of 0 also, okay? So you unite the domain constraints of the radical and the rational. This is what you have. If you want to isolate x, subtract 5 from both sides, you have negative 4x squared is greater than negative 5. Divide by negative 4, you have x squared is less than 5 over 4. And then you take the square root of both sides. And then you have the absolute value of x is less than root 5 over 4. That's basically the, oh, I'm sorry, if you root 4, you have 2. So it's root 5 over 2. If you root the numerator and the denominator. So you can write a domain like this, or you can write it as negative 5 over 2 is less than x, and x is less than root 5 over 2. So there goes your domain for this solution. Negative root 5 over 2. Negative root 5 over 2 is less than x, and x is less than root 5 over 2. Okay? You don't get any points in the scoring guidelines for doing this, but it's just cool just to know what the domain constraints are. All right, so that's that. Thanks so much for taking the time to watch this presentation. Really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. If you have any questions or clarifications or requests, just include it in the comment section below and we'll be glad to address it as soon as we can. More clips can be found on mathgotserved.com. Thanks again for watching. Have a wonderful day.